This is my favorite lecture on influence lines because this is where you get to learn the fun way to draw them. So up until this point, you've been using statics to develop influence lines. You've seen how to identify the key locations for unit load placement that make this process as efficient as possible, but it's still somewhat tedious. So now I'm going to show you another method of developing influence lines. It's called the Mueller-Breslau principle, and it's defined right here. As you'll find out, it's a lot faster and it's more fun. So essentially what this is saying is that if we make a modification to the structure according to which response we want to draw an influence line for, and then force that structure to undergo a unit deformation, also in accordance with the response that we want, then we can relate the deflected shape that results to the influence line that we're interested in. So the process, or this is best demonstrated through examples, but first it's important to define a few components of the process. So the first step in the process is to remove the ability of the structure to resist the design variable of interest. And that design variable of interest is whatever we want to draw the influence line for, a reaction or shear at a specific point or a moment at a specific point. Once we have removed the ability of the structure to resist that type of response, then we force the desired variable to move through a unit deformation. So for vertical reaction, this means we remove the vertical support and displace it upward 1 unit at that location. For shear, we want to remove the ability of the beam to resist shear internally. So what that means is we're going to effectively cut the beam at the location of interest and insert this roller guide. So we're going to cut the beam and add the roller guide to that location. This roller guide does not allow for any rotation or axial movement at that location, but it does allow vertical displacement up or down. So the displacement can be different between the two ends, right? So we're basically slicing the beam and then displacing it a unit total between the two ends. So I'll note here, we have no rotation and no axial deformation, right? I'm using the lowercase delta for that. No rotation or delta, only vertical displacement allowed. And then when we displace it by 1 unit, we want to make sure that we're doing it in the positive direction. And that's always going to be forcing the right side up and the left side down. This comes from our positive sign convention for shear, right? So if we have our standard shear segment with positive shear directions on both ends, if we pair 2 of those segments side by side, we see what the positive displacement would be on either side of a cut that separates the 2 segments. So This right here is what we're using. So we'll displace it by 1 unit total. I'll note all right, and we'll come back to that when we get to an example. For moment, if we're drawing the influence line for internal moment at any point along the beam, we're going to add a hinge at that location and then force it through a unit rotation. As you know, a hinge allows for rotation. The hinge can also displace vertically, right? But the two pieces have to stay together. So you can't have the differential displacement that we see in the roller guide. So I'll say add hinge and rotate 1 unit. And the positive directions for our rotation are going to be clockwise on the right side of the hinge and counterclockwise on the left side of the hinge. All right, again, corresponding to our positive moment sign conventions. After you've done that, then just draw the deflected shape of the structure. So for determinate structures, a few things to keep in mind is that the modified structure will be an unstable mechanism. And because it's unstable, the deflected shape will be all straight line segments. All right, and this is consistent with what we know about influence lines for determinate structure, right? We already know that the influence line has to be all straight line segments. For an indeterminate structure, the modified structure will be stable and the deflected shape will consist of curved lines. If it's not all curved lines, it's going to be mostly curved lines. All right, so it's important to note that when I'm talking about the unstable versus stable mechanism, we're talking about the modified structure, right? Because once you take away from a determinate structure, once you take away one response or one capacity of that structure, it becomes unstable. If you have an indeterminate structure, you can take away however many responses correspond to the degree of indeterminacy, and you can still have a determinate, or you can still have a stable mechanism. So for an indeterminate structure that's 1 degree indeterminate, we could take away, the ability for it to resist moment at a location by adding a hinge, and that would still result in a determinate structure that is stable. If we take away more than 1, then it would be an unstable mechanism. But for our influence lines, we'll never take away more than 1 response at a time. I should say we'll never take away more than 1 response per influence line. That's a more clear way of saying it. All right, so a few definitions before we move on to an example. we can have quantitative influence lines, which is a lot of what we've been doing so far with statics, right? For quantitative influence lines, you want to make sure that you include values at all the key locations. This is something that in this class we will always, or we can do for determinate structures. In your book, it goes through how to figure the values out for indeterminate structures too, but we're skipping that section, so it's not part of your assigned reading, and we're not gonna worry about that. So in this class, just determinate structures will have quantitative influence lines. Qualitative influence line means that you only have to draw the shape. Don't worry about the values in this class. We do that for both determinate and indeterminate structures. All right, so now we'll roll into an example. First example of the Mueller-Breslau principle. Here we have a determinate beam, all right? There's a hinge at B, and we have supports at A, C, and E. So the first item that we want is the influence line for the reaction at A. And I've noted on here with the highlighted location, the location of interest. So for the reaction at A, going through the steps, we remove the support at A, right? So that pin support is gone from this sketch, it goes away. And then we're gonna force the beam through a vertical displacement upward, right? That's a positive unit displacement at A. Now, we've done that. We draw the deflected shape that results from it. Looking at what's going on in the rest of the beam, we see that there is a support at C and a support at E. All right, so if we're drawing a deflected shape, the beam cannot displace at C or E. It has to have a zero displacement there. So those points must be zero. We also know that we have to draw straight line segments because this is a determinate structure. And the hinge is where the beam can change slope. So we can simply draw our straight lines according to what we've noted, right? In order for these 2 points to be met at 0, it has to be a horizontal line from B all the way to F. So that's it. Our influence line is done for the reaction at A. For the reaction at C, we remove the support at C and force it through a unit displacement upward, and then draw the deflected shape. So we'll just note that that's a value of 1 right there. We know that it can't move at the other supports, right? So those 0 points have to be maintained. And we know that it can only change slope at a hinge, right? We have straight line segments. The deflected shape has to have continuous slope except at a hinge. So from that, we can draw our straight line segment from B to F because there's no hinge between B and F. And then at B, we have that hinge, so it can change slope to meet the deflected, or to meet the 0 displacement requirement at A. So that is our qualitative influence line for the reaction at C. We've drawn the shape. We'll put numbers to it in a moment. Next up, we have the shear at D. So we've identified the location of interest, right? D is halfway between C and E, or it looks like it is anyway. When we put numbers to it, we'll find that it is. And we're going to cut the beam, insert that roller guide, and force the right side up and the left side down. Because this location is in between supports, both sides of that cut can deflect. So the right side of the segment, or looking at the right side of the cut, right, we know it's going to have a positive displacement, and then at the support it has to have 0 displacement. So we draw our straight line segment from D to F, right? There's no hinge between those locations, so we just have a straight line. And then from the other side of the cut, right, we have 0 at the support, and then we have a hinge right after that. So we're going to have another straight line. Just gonna copy and paste this one. Should work out. All right, another straight line segment between B and D. And then at B, we have that hinge, so it can change slope and meet the support condition at A. So that is the qualitative influence line for shear at D. And I'm going to go ahead and label some of the values that we will be finding in a moment. So going back to the reaction at C, we would call this RC when the unit load is at B. And then this point over here would be RC when the unit load is at F. This would be the shear at D when the unit load is at B, the shear at D when the unit load is at F down here. And then these points we'll call the shear at D when the unit load is immediately after the cut, and the shear at D when the unit load is immediately before the cut. I'll also note these distances, right? So we know that the total deformation has to be 1, right? So that means that the magnitude of A plus the magnitude of B is equal to 1. All right, so that's this distance right here is 1. So we're going to have to apply some geometry to figure out what those values are. And remember that that roller guide does not allow for rotation, right? Only vertical displacement. What that means is that the slope on either side of the cut has to be the same. So if the right side of the cut has an influence line slope of alpha, then the left side of the cut also has to have a slope of alpha on the influence line. All right. And then last but not least, the moment at D. So we add a hinge at D and force it through a unit rotation. If we force it through a positive unit rotation at D, that's going to make that hinge point move upward. So we're going to have a positive displacement at D, and that's a hinge, so it can change slope, which is good because that's the only way we can meet these support conditions on either side of it. So on the right side of the hinge from D to F, we have one straight line segment. And on the other side, we have a straight line segment between B and D, right? At B, we have another hinge, so we can change slope and meet the support condition at A. So this is now our qualitative influence line for the moment at D. We'll label these values MD when the unit load is at D, and MD when the unit load is at B, and MD when the unit load is at F. So breaking down a few items of the geometry here, All right, what we did is applied a unit rotation. So that's different from a unit displacement, a vertical displacement that we've been doing with shear and reactions, right? So that means this distance is not equal to 1, all right? So if we consider the total rotation at the hinge, all right, that would be this angle right here. All right, so that's going to be equal to alpha plus beta, which is 1. So we'll call alpha the slope of this line, and beta will be the slope of this line. So remember that it's important that this is a unit rotation. And that the vertical displacement at D is not the unit displacement. All right, so on the next page, we're going to talk through how to figure out the values on these qualitative influence lines. Some of them we already knew, right? For the reaction, actually for this reaction at A, we're all done because we have the unit displacement at A, and then every other point at every other key location is 0. For the reaction at C, we know the value at C, but we don't know B or F, so we'll have to find those. And then so on for the shear and moment ones. All right, so in order to calculate those values, we need to have some information, quantitative information about the span lengths. So now we have that added to this beam. And we've already gone through these steps of drawing the influence line. Now we're going to use the geometry to find the magnitudes of those values at the key locations. And then we're just going to do geometry to do this. So don't worry about signs, right? So emphasis on magnitudes. We're just going to find the magnitude, and then we'll assign plus or minus according to the shape of the influence line that we just drew. All right, so one thing to note here is that you always want to start at the location of interest. All right, so for the reactions, as I said, the reaction at A was already done. We just have 2 points to figure out for the reaction at B, or excuse me, the reaction at C, right? So going back to that influence line, we'll just make a mental note that from A to B and B to C and C to E and E to F is all 10 feet. So going back up here, we can see what we need are this point and this point. We have a triangle here, and a triangle here, and a triangle here. We can figure out the slope from this point, right? Slope is the same from B to F, so we're just going to use similar triangles to calculate those values. So to find B, we'll say the reaction at C when the unit load is at B over 20 feet should be equal to 1, which is the value at C, divided by 10 feet. So the reaction at C when the unit load is at B is equal to 2. And then for F, we apply a similar equation, right? Reaction at C when the unit load is at F over 10 is equal to 1 over 10. And here, right, don't worry about the fact that this is a negative value. We know it's negative. We're just getting the magnitude. All right, so we know the magnitude is 1. We'll just assign the negative based on the shape. For shear, I've got the location of interest kind of copied here in a sketch for convenience. So for shear, we have two pieces of information that we need to work with, right? So one is we know that the magnitude of A plus the magnitude of B is equal to 1. All right, so that's one equation. And then another equation, because we have two unknowns, so we need another equation. The other equation is that we have continuous slope. All right, so that means that alpha is equal to beta. I think on the previous page I drew them both as alpha, but we're just noting that we could call them two different angles and then establish that they're the same. So that follows then that the tangent of alpha is equal to the tangent of beta. All right, the tangent of alpha would be A over 5 in this case. And the tangent of beta would be B over 5. So from those two equations, we would get shear at D immediately before the cut is equal to B, which is negative 0.5. Again, only magnitudes are needed in the equations. We know it's negative because of the way we drew the influence line. And then immediately after the cut, we would have positive 0.5. Now that we know these 2 points, we just use the similar triangles to find the remaining values. All right, then for moment, again, I have the location of interest resketched here. So we're just going to find first the value at D, and then once that is found, you can go on and use similar triangles to obtain the remaining values. All right, so we again need two equations, because this time our two unknowns are the angles on either side of the hinge, right? So we need to know alpha and we need to know beta. So our first equation is going to be that of the unit rotation. Alpha plus beta is equal to 1. Our second equation is going to come from applying the small angle theory. So we can say that the tangent of alpha is equal to alpha, and the tangent of beta is approximately equal to beta, right? So we'll just call that small angle theory. And this first one comes from unit rotation. So from those two equations, we write the moment at D, when the unit load is at D, divided by 5 for tangent of beta, or alpha in this case. They're the same. Plus the other side is equal to 1. And then solving, we'd get 2.5. All right, so now that we know D, we can find the remaining values using similar triangles. So I'll just note. All right, so that's applies to both. All right, a few more examples that we'll do. Same beam. We're just going to get a little bit more into it. So for shear immediately before the support at C, we identify the location of interest, insert the roller guide, and in this case, we want to push the right side up, but there's a support there, so it's not going to budge. So that means the left side is going to displace downward the full unit displacement. Now, in order to draw the deflected shape, we have to recognize what's going on either side of the cut, right? So we just established that the right side of the cut isn't moving because there's a support right there. So the next thing to the right is another support. In order to maintain straight line segment, that has to be a horizontal line with a slope of 0. We have to have the same slope on both sides of the cut. So from the hinge to the cut, we also have a 0 slope. All right, and this value is -1 because it has to be a unit displacement total. And then at the hinge, we can change the slope to meet the support condition at A. Now that influence line is all done, qualitative and quantitatively. For shear immediately after the support at C, move the roller guide to the other side. Now the left side can't move because there's a support right there. So the right side has to take the full unit displacement. All right. So this is going to be a value of 1. And then we draw the straight line segments. So on the right side of the cut, we just have one support condition to meet. So we can draw a straight line with a negative slope. And then on the other side, we have to match the slope. That's not what I wanted to do. Copy, paste. There we go. So we match the slope, but only to the hinge. At the hinge, the slope will change. And all of our support conditions are met. Now, to finish this influence line, right, in this case, the geometry is pretty easy. So with all the spans being equal to 10 feet, right, this value will be 1 and this value will be -1. For the moment at C, we keep the support, right, because we're just drawing moments, so we're adding a hinge at C, forcing it through a unit rotation. Now, when a hinge is between supports, a positive unit rotation will force that hinge to displace upward. But now that we have a hinge at a support, it can't displace up or down. So we need to keep that in mind when we draw the deflected shape, right? So the support conditions still have to be met. So on the right side of the hinge, we have 2 supports in a row, right, including at the hinge. And so that has to be a 0 slope influence line. On the left side of the hinge, the next thing we have is another hinge. So the left side of the hinge is going to have the full unit rotation, and that counterclockwise rotation will force the beam to deflect downward on that side. So it will deflect downward until it reaches the slope, the hinge at B, and then change slope to meet the support condition at A. Now, since alpha is equal to 0, beta has to be equal to 1. All right? And then to calculate the moment at C when the unit load is at B, all right, we're going to do a little math over here. So we know alpha plus beta is equal to 1. Alpha is equal to 0, so beta must be equal to 1. And then from small angle theory, we can say tangent of beta is equal to beta. So the moment at C when the unit load is at B divided by 10, right, this distance of 10 feet, is our tangent of beta, so that's going to be equal to 1. So we find that the moment at C when the unit load is at B is going to be -10. And we'll write it on the influence line, because that's the easiest way to see the values. All right, and then last one, shear at B. B is the hinge. So this one is a little bit weird, because now we already have a hinge, right? So it can rotate, and then we're adding a roller guide so it can displace vertically. All right, we're going to force the right side up and the left side down. Now looking at what's going on either side of that hinge and roller guide cut, we have support conditions, all right, 2 roller supports on the right side. So the segment between those 2 supports has to be a straight line, right? And it has to be horizontal. And there's no hinge until we get to B, so that whole span from B to F has to be the straight line segment. All right, so that means our slope is equal to 0 on the right side. Now, normally for shear, we would have to match that slope on the other side, but because the location of interest is at a hinge, the slope can change. All right, so since the slope is 0 from B to F, that means that it does not displace on the right side, which means the left side takes the full unit displacement, and it rotates because there's also a hinge there. So this is our influence line for shear at B, which is also a hinge. So this one's kind of weird. But that's the only exception to the rule that the slope must be the same on both sides of the location of interest for shear. All right, now we get into indeterminate beams. These are even more fun and more easy to draw because we don't have to worry about values. So all we are doing is drawing the shapes. And remember that when we take away one capacity of an indeterminate beam, it's still going to be a stable structure. So for this indeterminate beam, we don't have any hinges to worry about here. we just have a bunch of vertical supports. We're going to just go through and draw the influence lines. So for the reaction at A, we have roller supports at B, C, D, and E. So we're going to make sure that we maintain 0 displacement at those points. We remove the support at A, force it through a unit displacement. That's going to look something like this. Right, for the reaction at B, I've highlighted the locations of interest on each of these lines here too. I think in your version you should also have the supports drawn in where they remain for each influence line. I forgot to add that in my version, but it's always a good idea to draw those on to remind yourself of these 0-point locations. So for the reaction at B, we keep all the supports except the one at B. All right, so these points all have to be 0. And then we force B through a positive vertical displacement. So that's going to look something like this, drawing curved lines. For the moment at F, we have all of our supports in play. And we're going to add a hinge at F with a positive unit rotation. Since the hinge is between supports, a positive rotation will force it upward. Now on the left side of the hinge, this portion of the influence line is just going to be a straight line because this segment from A to F on its own is vertically unstable. The rest of the beam, right, the other side of the segment, is stable on its own vertically. So this will be all curved. Not like that. That's close. For the moment at C, we have all of our support conditions must be met, including the one at C. All right. We're going to add a hinge and force it through a unit rotation. So the hinge at C cannot displace up or down because the support condition must be met. On the right side, that clockwise rotation will force the beam to deflect downward. We have curved lines because if we isolate this segment, all right, we'd have a roller support here, a roller support here, and a roller support here. That is vertically stable on its own. On the left side, if we isolate that segment, we have 3 roller supports, which is vertically stable on its own. So this will also be straight line segment, curved segment. And that counterclockwise rotation will also force it to deflect downward. And then if we want to draw the influence line for a shear at F, we add that roller guide to F and force it through a unit displacement, right side up, left side down to total 1 unit, but we don't really have to worry about the values. We're just drawing the shape. All the support conditions must be met. So we draw curved line on the right side, and then similar to this guy up here, the segment from A to F is vertically unstable on its own, so that portion will just have a straight line. And then if we draw the negative moment at C, all right, that's really just drawing the reverse of the positive moment at C. So we have all those support conditions that are met. We just change the direction of that unit rotation. All right, so now on either side of that hinge, the beam would deflect upward instead of downward. All right, so now one of the things that influence lines are really useful for is identifying what spans to place live loads or environmental loads for your analysis to generate the worst case for a specific response. So I'm going to highlight those locations for each response in pink, and we'll just go through this. For the reaction at A, right, we have two spans that have a positive influence line and two spans that have a negative influence line. The responses that are closest to the location of interest is going to have greater magnitude, right? So the magnitudes will dissipate the farther away you get from the location of the response. So we can confidently conclude that A, B, and C, D will have the placement of the live loads to maximize the reaction at A. So I'll just note this pink highlight represents the placement of uniform live load to maximize response. For the reaction at B, this one's pretty straightforward too. We would definitely want to maximize that positive span from A to C, and then the positive span from D to E. All right, so that would be where we would place those live loads. Now, sometimes, right, maximizing the response doesn't necessarily mean putting it on the positive spans. It could mean putting it on the negative spans. It depends on the response that you're looking at and the configuration, right? So for the moment at F, place that live load from A to B, and then from C to D, C to D. For the moment at C, right, so now we would place that live load on the two negative spans because those are the ones that are closest to the location of interest. They'll have the greatest magnitude there. For the shear at F, this one is a little bit ambiguous, right? So without really knowing more details about the span lengths, the way they're drawn, it's assumed that these are equal span lengths, and this is roughly, right, half. F is halfway between A and B. So if we make that assumption, right, we could say the most likely maximum response will come from the negative spans because we have more of those. So we can say that, the negative spans. All right, so that would maximize the negative shear at F. And then if we wanted to maximize the positive shear at F, we would place it over those two spans, right? But the negative shear at F would probably have a greater total effect that can be achieved based on this influence line. All right. Now, the last two pages, this page is a good example because it demonstrates what to do or how to draw influence lines for a lot of different responses, for a determinate beam and then an indeterminate beam with fixed supports. All right, so that's one thing we haven't really gone into yet with this method. But the key thing to remember with a fixed support is that your deflected shape, when you draw it, can't have any rotation at that fixed support. So the only exception to that would be if you are drawing the influence line for the moment at that fixed support. So I'm going to add that one right here. All right, so if we're going to turn this sketch into the moment at A influence line, then what you do is you effectively change that fixed support to a pin support. All right, so that's the same thing as adding a hinge to the fixed support, right? You're just taking away the ability of that support to resist rotation. So we're changing it to a pin and then forcing it through a unit rotation. The positive direction would be clockwise on the right side of the support, which is where the beam is. So that would force this beam into that shape, right? Meeting those support conditions at C and E and also at A, so it can't deflect vertically at A. So that's the only exception. You'll see all of these other influence lines for this beam have zero slope at A, right? And in the determinate version of the beam, which is a similar configuration just with two hinges added, it's similar, right? Except you have straight line segments. And so whenever you have, a support or two supports in a row, right? Or the fixed support followed by a hinge, right? Even though this hinge can rotate, this piece cannot. So the fixed support has to have zero rotation, right? So that's highlighted here. No rotation at A. You have to have that horizontal slope at A. So you have to think about what that means for the rest of your beam. In some cases, it means that you have a long stretch that's just horizontal. Now this one does have, I skipped over it, this one does have the moment at A shown. I think over here I replaced it with the negative moment at C. But other than that, all of these should match comparing the determinate to indeterminate. So again, you can see here at the moment at A, you remove the fixed support, replace it with a pin, force it through unit rotation. So that's going to cause the beam to deflect downward here. Since there's a hinge right after it, we can have that displacement at B, right? Or, yeah, the hinge is at B. So you end up with this shape, and this is the only exception, right, to all the other ones which have zero slope. All right, now bonus, we have qualitative influence lines for frames. So this is also touched on in your textbook. Basically, with frames, you start off the same way, right? Depending on what response you're looking at, you'll probably have a mid-span moment or a mid-span shear. We probably won't do reactions because that would be just similar to next to joint shear. That would be kind of the same thing there, or very similar anyway. So for mid-span moment, just add a hinge at the middle of the span, right? So we're drawing the influence line for the moment at this point in this beam. Force it through a unit rotation. That would force the hinge to displace upward, and then draw the deflected shape. When you do that, you can treat these joints between beams and columns, you can treat those as supports, all right? With the caveat that rigid joint behavior must be maintained. So that means columns, all right, have to sway or have to rotate by the same amount and in the same direction that the beam does. Right? You have to keep that 90-degree angle between beams and columns. So these influence lines that are drawn in these examples are incomplete because it's only showing the beam line at the level where the response is found. We need to have curved lines on all beams and all columns. So in order to do that, you start with that location of interest, draw the influence line for that beam line, treating those joints as supports, and then note the rotation at each joint and what direction it's going to be. That will tell you how to draw the column influence lines. And make sure to pay attention to the support conditions at the base, right? So at a pin support, you can have rotation. At a fixed support, like down here, you can't. So you have to make sure that you show that clearly. And once you've drawn all of the column line curves, then note the rigid joint rotation at every other joint in the frame. And finish your influence line with the beams. All right. Now I'll demonstrate the midspan shear as well, because this introduces kind of a different behavior that we haven't seen yet. And so, right, we're cutting the beam a midspan, forcing the right side up and the left side down, drawing the influence line using curved lines and treating those rigid joints as supports. Noting the rotation of each joint, we'll then use that to draw the column curves. And your sketch doesn't have to be perfect, it doesn't have to be pretty. It just needs to show the correct rotations of joints. All right, and whether your displacement is positive or negative for a beam, to the left or the right for a column. So what we're gonna find when we do the beam influence lines then, and I'll just draw the top one, is that in this center span, which aligns with the location where we cut the beam on one level, we now have the columns rotating in the same direction on either side of that span. So in order to meet that slope condition, that beam has to be in double curvature. So we get that S shape there. And we're gonna see this on all of the other levels, right? So it's gonna look like that. So your final challenge is to complete the frame influence lines below here. So these are next to joint moment and next to joint shear. See if you can figure out the rest of the frame, and I'll just talk through these points a little bit, right? So next to joint moment, we would add a hinge right next to the joint, force it through a unit rotation. Because it's right next to the joint, it's not going to deflect, right? So we treat that as a vertical support. And on one side, it'll rotate clockwise, and on the other side, it'll rotate counterclockwise, which will force it down on both sides, not very unlike a beam with supports, right? So you can just kind of treat this as an indeterminate beam. Now, where you have to think a little bit more is one side of that hinge is going to be attached to the rigid joint still. That rigid joint has to rotate in the same direction as the beam did on that side of the hinge. So the rigid joint will also get that counterclockwise rotation. For the next to joint shear, right, we would cut the beam right next to the joint and force one side up and one side down. One side is going to be free to displace, right? In this case, that's the upward direction. And so we just draw that influence line like we would for an indeterminate beam. The other side, in this case the left side, wants to go down, but it can't because there's a joint there. So we treat that joint as a support, draw that influence line, right? The slopes would match, right? So again, your sketch doesn't have to be perfect, but we remember in our heads that the slopes here match. So that means that it's got to be an upward deflection, right, in order for the slopes to match. You can't have a downward deflection and the slopes match. And then the side, again, that is attached to the joint still will dictate what direction the columns will rotate, all right? All right, so that ends the lecture on influence lines using the Mueller-Breslau principle.